Yo, what is up YouTube? In this video, I wanted to teach you a little bit about operational amplifiers, also called op amps. So there's two inputs to these sorts of devices. We have the non-inverting input, which is labeled V plus and goes into the plus terminal. V minus is the inverting input and then goes into the negative terminal. And then we have our power supply supplying the op amp. Sometimes we have a plus and a minus here. Sometimes we just have the plus and then at the bottom we have ground. A lot of the times when we're doing these problems though, we'll not have these included because they take up some space on the paper. And then of course we have the output to our operational amplifier. Now if we're making some assumptions about the operational amplifier, we call it ideal. And those assumptions that we often make are that there's high input impedance. So you can think about that as if we had our op amp here. What's coming in is going into a giant resistor, think like giga ohms, and then going to ground. So no current's going to want to flow through these leads is basically what we're saying with that. The next thing is that if V plus is greater than V minus, then V out goes up. And if it's the opposite, if V minus is greater than V plus, then V out goes down. The first thing that I like to do is talk about the voltage follower. This is our first example of negative feedback, and it's a nice example. So let's think about what happens if V out is greater than V in. So in that case, then V minus is greater than V plus. So V out will decrease. And we see a decrease down towards V in. Now, what about the case where V out is less than V in? So if this is less than V in, then V minus is less than V plus. So V plus is greater, so V out will increase. And what happens here is you have this subtle game where your V out chases your V in. It goes like that. And this is also called a voltage follower. So our gain here, V out over V in, is equal to 1. So V out equals V in. That's why it's called a voltage follower or a unit gain amplifier. Something with this that's interesting, it doesn't seem like a very useful circuit, but it is because you have really high input impedance here. Cool. So that'll help us uncover a rule here. If you have negative feedback, your negative terminal and your positive terminal will be equal. And that's not enforced because there's some grounding mechanism inside the op amp. That's enforced by the output. The output guides the negative input towards the positive input. That's why V minus is assumed to be V plus in these problems. So let's take a look at the inverting op amp scenario. So we see here that the positive side is on the bottom. It's okay to put it there. And we have this voltage here, plus to minus is 0 because it's connected directly to ground. Now, since we said V minus and V plus are equal to each other, we can place 0 volts here too. Now, the other assumption here is that the current coming in through here is 0 amps because there's high input impedance, right? So what we can essentially do is deconstruct this circuit. We have something that looks like this. We have V in, and we have R1. We have a branch that comes off towards 1 giga ohm. So basically 0 current comes through here. And then we have R2. And at the end of R2, we have V out. So what I like to do here is just cut off this 0 amp spot. No current's going there, so it's not useful to our circuit. Now we have V in here. And remember we said right here in between R1 and R2 is 0 volts. So something we can do is do V in minus 0 volts over R1 is equal to our current. So our current flowing this way is equal to I is equal to V1 over R1. Nice. So that same current is going to be flowing through here because they're series resistors. So we have 0 volts minus V out over R2 is also equal to I. So we have two equations here that are equal to I. We have V1 over R1 is equal to negative V out over R2. Now if we rearrange to get V out over V1, we get negative R2 over R1. And that is our gain. And it's called an inverting amplifier because we have this negative sign here. Cool. Let's take a look at another example. So here we have a similar scenario. This is 0 volts. So this is 0 volts. Nice. So since this is 0 volts and these all share a node, each of those is 0 volts. So the current here, here, and here. So let's call this I1, I2, and I3. I1 is going to be equal to V1 minus 0 volts over R1 equals V1 over R1. Then you can follow that I2 equals V2 over R2. And I3 equals V3 over R3, right? And then with that, the sum of the currents coming out of this node is equal to IN. IN equals I1 plus I2 plus I3. Okay, so that's nice. We know that same current, none of it's going this way. So all of it's going through this resistor. We'll call that IN still. So we have this relationship. We have 0 volts at this node and then V out at this node. So 0 volts minus V out over R4 is equal to I in. And we have our I in equation here. So we have negative V out over R4 equals I1 plus I2 plus I3. And remember, we solved that those are going to be V1 over R1, V2 over R2, and V3 over R3. So we have negative V out over R4 is equal to V1 over R1 plus V2 over R2 plus V3 over R3. Now rearranging, we can solve for V out in total. So V out is going to be equal to negative R4 times V1 over R1 plus V2 over R2 plus V3 over R3. So you could imagine what we can do here is change the values of R1, R2, and R3 in order to weight how much each of those things are summed together. So that's kind of interesting. And one example that my teacher gave me was maybe if you had 3 people playing guitar and you wanted each of them to have a certain amount of volume, which is that gain, then you could have them go into the summing amplifier. Obviously now they do a lot of digital stuff. It's a lot outdated, but there's still some cool applications you can do with these operational amplifiers. The last one we'll look at for today is a non-inverting amplifier. So this one's a little bit different. Our positive terminal is no longer connected to ground. So what we have is Vn is here, right? Because Vn is here and the negative terminal goes towards the positive terminal. Okay. And we know that the current here is 0. So this current equals this current. Now what is that, this current here? We'll call it I. I is equal to I. I is going to be equal to 0 volts, the left of the resistor, 0 volts, minus V1 over R1. Nice. And now, similarly, we can write the current across this resistor as Vin minus V out over R2. And that's also equal to I. So what we can do is set those two together. set those two equal to each other, we have negative Vn over R1 equals Vn minus Vout over R2. All right, now what we can do here is multiply both sides of the equation by R2. So we have negative R2 Vn over R1 is equal to Vn minus Vout. Now what I can do here is move this Vout to this side and move this to this side. And we have Vout is equal to Vn plus R2 Vn over R1. Now let me move this over so I can finish on the right hand side. So we have Vout is equal to Vn times 1 plus R2 over R1, just factoring out that Vn. So now we have Vout over Vn is equal to 1 plus R2 over R1. Nice. So this is really cool. This gain here is always positive. It's not inverting like our last case, but we can talk about what our bounds can be. So I guess you could say R2 could be 0. So this gain could go from 1 up to, you could have R2 over R1 be infinity. If you had R1 be 0 and R2 be large, or R2 be somewhat large and R1 be 0, you could get this range of gains 0 or 1 to infinity. And that's not always what we want, because we might want values that aren't unity gain. So like if we wanted like 0.2 gain or something like that. So what we can do usually is cascade two inverting amplifiers. So recall that this has an output negative R2 over R1. So if you made R2 equal to R1, then you get a gain of -1. So you invert it. So if you follow this amplifier up with the same amplifier with R1 and R2 equal to each other, then you could get your output to be whatever this gain was in terms of making it positive instead. So that's pretty good stuff. Hopefully this video kind of demystified some of the things that you've run into while working with these operational amplifiers. And I hope you enjoyed this video in total, and have a wonderful day.